Hello, and welcome to College Algebra. This is a short video intended to get you started with the materials you'll need for the class and give you an overview of what we're going to be doing this semester. I'm Nathan Rafus. You can reach me at this email address here. I'll always be available to answer emails. We're going to be learning a little about algebra this semester. And I'll tell you why in just a minute, but first I want to give you a quick warning. This class goes really fast. This is a lot like Algebra 2 in a high school, except that in a high school setting, Algebra 2 is a year-long class. You have 30 weeks to learn the material. Now, here at UWG, in the summer or in the spring or the fall, we do this class in 15 weeks, so twice as fast. But this is a summer semester. We're going to be doing this class in 7 weeks, so it'll be going about 4 times as fast as high school. That just means, hopefully, since it's the summer, you have fewer other obligations. You're going to have to put in maybe 10 or 15 hours a week studying for this class. If you want to do that all at the beginning, that's a decent idea. Probably not a great idea to save it all for the end, but up to you. It'll all be available until, I want to say, July 23rd is when this class ends. There's a few websites I want you to be aware of. These are where you're going to get your resources for this class. First off, our textbook is free. It's on openstax.org. Myopenmath is where we're going to be doing all of our homework. I'll show you how to set that up in just a second. And here on CourseDen is where you're going to find your lectures, your lecture notes, and the syllabus. I think later we'll have our final exam here as well. So let me show you these websites. Here we go. So first off, there's OpenStax. This is what it looks like when you go to their webpage. And they're a repository of free textbooks. So we're going to go to Subjects and select Math. And our textbook is this red one here, Algebra and Trigonometry. You can view it online, but the PDF download is a little bit cleaner and nicer to use. So you'll click that. It's going to take a minute to load because this is a few hundred megabytes. But here's what it looks like once you get it loaded. So we've got algebra and trigonometry here. We're not going to do the trigonometry part, just the algebra part. So we'll start by talking about exponents, radicals, scientific notation. That'll be Unit 1. We'll get all the way through the Cartesian plane in Unit 1. This textbook is a nice reference. It's got, at the end of every section, it's got practice problems. So for example, if you need to brush up on complex numbers, which we'll be learning in Unit 2 to get us started on solving polynomials. We have online homework on Myopenmath. I'll show you that in just a minute, but these exercises at the end of the chapter are great if you need a little bit more practice. If you need to work on these, a good thing to do would be to come to my office hours. Those will be virtual. Those will be on Collaborate Ultra, just like this video. Try to work some of these problems on your own, and then bring your work to my office hours, and we can go over it together and see how you're doing. That's a really good way to learn in this class. But that's our textbook. Let's see. Next website is Myopenmath. This is what our course page actually looks like on Myopenmath. I'll show you how to get here in just a moment. But you're going to be having this is the biggest component of your grade. 40% is solving all of the problems. So for example, if I go to functions, functions are really useful. They're a way to abstract a method. So a function says we're doing something to a number, and each function is a different thing we can do. So you can look through the questions. Where's a good one? I'm looking for one that okay, so this assignment is a little bit different, but some assignments will have you answer questions like yes or no. Some of them will have you type in your answers. And the cool thing is, if I put in a wrong answer, okay, got to get the syntax right. It's going to say, well, we got the yes or no question right. We didn't get this answer right. You get unlimited attempts. There's no penalty for guessing. And you get instant feedback as to whether your answer is right or wrong. So the correct answer for this problem is from negative infinity to, looks like -1 is the domain of this function. It's all the x values where it's defined. And and I need a square bracket here. Don't worry, we'll learn those rules later. And see, now I've got 2/3 of the points for this problem. So now I just need to answer this question, and we'll have all the points. So Myopenmath is a nice instant feedback kind of environment where you can try to work out what you're doing. You get unlimited attempts. If you do more than 5 or 10 attempts and you still can't get the answer right, don't frustrate yourself. You have all semester to get these done. Just bring it to my next office hours and I can give you some hints or some guidance. Now, I started on my landing page for as if you were already logged in. Let me show you how to create an account real quick. We're going to hit register as a new student. This is what the landing page looks like for Myopenmath. You'll type in a username, you'll choose your password. Please put in your actual first and last name here. And then give me your UWG email address. The most important thing is our course code is 74076, and you leave the enrollment key blank. So after you've filled out all of this information, you put in the course code of 74076, you leave this next field blank, and then you can hit sign up, and that'll get you started. So that's how you access our homework. Your unit tests are also going to be on this website, and we'll go over that more once it's time for the first test. Let's see. So the only other web page I haven't showed you yet is, well, you're already here, hopefully, Coursden Collaborate. You can view any of my lectures by clicking recordings here. Right now we just have an introduction to the class recorded, but all of my lectures for the semester, how to solve each of the problems, introductions to all the subjects will be organized here nice and neatly. Or if you just want to look at the whiteboards for the lecture, you could go to content here, and it's empty right now, but by the time you're seeing this, there'll be my notes, my whiteboards for each of my lectures will be down here, as will be the syllabus, which is where you can find all the stuff I'm telling you right now and a little bit more detail. So those are the 3 websites that we need to be aware of for this class. Most of your work is going to be taking place on Myopenmath. Most of your instruction is going to be coming from Coursden. Let me switch back to my notes here. Okay, for the last part of this video, I want to talk briefly about what my goal is for you for this semester. I know that your goal is to pass the class and move on with your degree, and I'm aware that not all of the concepts that we study in this class are going to be relevant to your careers, but it's more the way of thinking that's going to be relevant to your lives. So one reason we study algebra is that the real world is shaped like algebra concepts in a lot of different places. If you can assign numbers to a problem in any way, you can probably use this class to learn some information you didn't already have. Like, how long will it take my car to slow down from 70 miles an hour? Or how big of a spring do I need to put in this machine to keep the parts contracting correctly? Or how far away will these magnets have to be before they stop attracting each other? As a matter of fact, the answers to all 3 of those questions are the same quadratic equation. It's 1/2 x squared is the equation for all of those. So math is pretty neat in that we can learn a lot of things about the real world by doing math. But more importantly than that, I want you to understand how math does and doesn't work. So independent of any actual application, if you get a feel for the way that mathematics behaves, it's such a big part of the real world that that'll give you a better feel for how the real world can or cannot behave. I want you to internalize the kind of analytical approach to solving problems that we'll be learning over the course of this semester. And that's really important because I think a lot of people come into this class believing the myth that they are bad at math, quote unquote. I don't think bad at math is a thing. Maybe you haven't practiced enough math, but anyone can get good at math. Because intelligence isn't a number that you're born with, it's a structure that you're building onto your whole life. And adding mathematics to the structure is going to make the whole thing more efficient. That's my main goal for you this semester. I want to talk about a couple of big themes that I'm going to be returning to several times throughout this class. First one is syntax versus semantics. This is two different ways to learn math. I think the naive way to learn math is by syntax alone. Syntax is like the grammar of a language. So if you come into this class with the mindset that you need to memorize all of the symbols I teach you, solving problems is a matter of memorizing a series of steps and then working them out on your paper, and then the last line of your computation will be a symbol that represents the answer. That's a syntactical understanding of the class. You just memorize the words in this language of mathematics, memorize all the rules of grammar to get from one line to the next. And you can probably solve every problem this semester without learning an ounce of what any of these things actually mean. But that's going to take more effort, it's going to be harder to remember, and it's not going to be as useful later. So the way that I like to learn is by semantics. If syntax is the grammar of a language, semantics is the meaning behind it, the meaning of the words, the meaning of the sentences. Mathematically, in this class, what I mean by semantics is I want you to try to get a feel for the mathematical objects that we're studying, manipulate them to learn what you want to know from them. I think that mathematical objects are real things, and I want you to try to interact with them as directly as possible to try to understand how they behave. That's my main goal for you this semester. So as you're trying to learn semantically, you could ask this object that the professor's teaching me about, what is it like? How does it work? You could ask, why does this thing work? Mathematics is neat in that it's consistent. As long as you're applying the mathematical method correctly, you're always going to get the right answer, and it's going to agree with any other method we can use to solve that problem. So you might ask, why does this method always produce the correct answer? Or even better, why doesn't it ever give the wrong answer? Is there any way I can break it? Can I put in weird inputs and try to give me nonsense? Playing around with the concepts like that is a great way to understand them deeper. You could ask if this method agrees with other methods you've learned to solve the same problem. And probably the best thing you can do for yourself is ask, why does it agree with those other methods? If you can understand why there's symmetry between this method and another method for solving the problem, you're going to have a very deep understanding of that problem. It's going to stick with you for a lot longer than if you just had a syntactical understanding. It takes less effort to learn if you understand what the things you're learning actually mean, rather than just trying to memorize a whole lot of abstract symbols. And learning semantically is going to be a lot more useful in cross applications, because maybe you never have to compute how long it takes a falling object to hit the ground, but if you get a feel for the quadratic equations behind it, they're going to be useful to you in a million different places. They show up all over the world. So you might never use any of the specific applications we study in this class in your job or in your life, but if you get a semantical understanding of how they work, that's going to come back to assist you later in life for sure. I use math every day, not just in my job, but in my life. Let's see. Then two themes I'm going to go over regularly throughout the semester are symmetry and emergent complexity. First, symmetry. If you take a look at maybe a capital A here, this thing has horizontal symmetry. The left half of the letter A is a mirror image of the right half of the letter A. That's the common English definition of symmetry, right? If you put a mirror up to the middle, the left side and the right side look the same. In mathematics, symmetry is a lot deeper than that. The idea is that if I only look at the left half of the A, I'm getting two pieces of information for the price of one. One, I know how the left half looks, and two, because I know it's symmetric, I know how the right half looks. Mathematics is full of different places where you get symmetry like that, but more abstract. Like maybe if I know how this function behaves in the negatives, that gives me information about how the function behaves in the positives. That's a form of symmetry. Or maybe if I know how to use geometry to solve this problem, that can tell me something about how to use algebra to solve this problem. That's a form of symmetry. Mathematics is full of cases where we get multiple pieces of information for the price of one. In fact, mathematicians like very much to look for those things. we don't like to solve one problem at a time. We like to solve whole classes of problems. That's called abstraction. So maybe you tell me, John goes to the top of a hill and throws a rock off. The hill is 100 feet tall. How long does it take the rock to hit the ground? I could crunch numbers and just solve that problem. But then tomorrow, if you say, Jane went to the top of a different hill, it was only 60 feet high. How long does it take her rock to hit the ground? If I solve John's problem in the abstract, then I don't have to start all over. The abstract would be to say, okay, let's say the hill is h feet high. How long will it take to hit the rock to hit the ground? What's the process I do to h every time to get that answer? And once I know that process, then on the third day, if you tell me that Shelley went to the top of a 120-foot hill, I can give you the answer right away. As mathematicians, we're always looking to solve whole classes of problems so that we don't have to do redundant work later. That's a form of symmetry as well. So that's going to be a big focus this semester is, rather than solve one story problem, can I develop a method that lets me solve a million different story problems? Last thing I want to talk about a lot this semester is emergent complexity, mainly just because I think it's really cool. It's the idea that you can start with a simple definition and end up with very complicated behavior. And mathematics is full of things like this. Complexity is not a conserved quantity. I can start with something. In fact, our next lesson is going to be, I'm going to start with just a handy shortcut for repeated multiplication. I don't want to write 2 times 2 times 2 times 2 times 2 on my page every time I have 5 2's to multiply together. So I'll call that 2 to the 5th power. So exponents are going to start out as just a handy shortcut in our notation. But what we're going to do is say, well, if this shortcut works the way we want it to, if it follows that simple one-sentence definition, what can we learn about the way that exponents behave algebraically? And we're going to develop a really intricate quiver of tools we can use to simplify expressions involving exponents, all of which come right back to that definition. There's no other source of the complexity. It's like this one definition unfolds into a beautiful, intricate shape of mathematics. Everything we do this semester is going to follow that pattern. Mathematics is one of the best places to look for emergent complexity. So I just want to make you aware of that because for me, it's one of the most aesthetically pleasing things about mathematics. All right, I think this video's probably gone on long enough at this point. So join me soon and we will talk about those exponents. We'll get started on the material. See you around.